Good afternoon, everyone. My name is Sonia DeBulio, and I'm the Director of Alumni Relations for this great faculty of Applied Science and Engineering. I want to thank each of you for being here with us today for our very last school lunch and learn presentation for the 2021-22 season. It's actually hard to believe that we got here. We have alumni tuning in from all over the world, as I was saying earlier. We have guests joining us from 8 different countries, including Canada and the US. We have Ethiopia, Hong Kong, Mexico, Singapore, Trinidad, Tobago, and the UK. Welcome. For those of you new to the Lunch and Learn, did you know that the Lunch and Learn was actually founded by the class of 1935? It came out of necessity. After they graduated, it was tough times finding jobs. So this group used to meet monthly at Fran's Restaurant on College Street to network and see what opportunities were out there. And the rest, as they say, is history. Before starting today's presentation, I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still home to the many Indigenous peoples from across Turtle Island, and we are grateful to have this opportunity to work on this land. A quick housekeeping item, at the end of today's presentation, we will have time for formal Q&A. Should you have any questions for Professor Tushi, please submit them using the Q&A button at the bottom of your Zoom screen. For the individuals who submitted the questions during the registration period, we've shared those questions with Professor Tushi before today's presentation, and she'll attempt to answer them either throughout the presentation or in the Q&A period. And with that, it gives me great pleasure to introduce our MC and chair of the School Lunch and Learn program, Laurie Hivala. Laurie is not only an Electrical 65 grad, he is also one of our most dedicated and engaged members of our alumni community. Laurie has been chairing the School Lunch and Learn program for several years and continues to generously dedicate his time to maintaining our School Lunch and Learn's long established traditions. And with that, please join me in welcoming Laurie Hivala, who will introduce our speaker for today's event. Thank you.
Thank you, Sonia, for your very warm introduction. It is my pleasure to welcome our guest speaker, Professor Marianne Touchie. Today, she will be discussing numerous performance issues and challenges associated with contemporary residential buildings. In addition, she will explore some of the novel approaches to reduce energy consumption and associated carbon emissions. Marianne Touchie is an assistant professor jointly appointed in the departments of Civil and Mineral Engineering and Mechanical and Industrial Engineering here at the University of Toronto. And she's also director of the Building, Energy, and Indoor Environment Lab. Dr. Touchie's research team focuses on improving the energy performance and indoor environmental quality of existing buildings to make them more comfortable, healthy, and sustainable through comprehensive retrofits. This work includes field monitoring of building energy performance and indoor environmental parameters, as well as occupant behaviors and perceptions through her surveys. Much of her research has been in the high-rise residential sector and particularly social housing buildings. Dr. Tushi is also the president of the Building Science Specialist Board of Canada and the former chair of ASHRAE's Technical Committee 2.1 of Physiology and Human Environment. She is also the most recent recipient of the Faculty of Applied Science and Engineering's Early Career Teaching Award, for which we congratulate her. And now, without further ado, please join me in welcoming Professor Marianne Touchie.
Hi, everyone. Good afternoon. And thank you so much for the warm welcome. So delighted to be here with you today. I'm just going to pull up my slides and we can get rolling. So yeah, anyway, really delighted to be here. Thank you so much, Laurie. And let's take it away. So today I'm going to talk to you a little bit about my research and my area of interest in high-rise housing. This is something that I've spent the last decade or more now researching, and love to share some thoughts with you today. So in our class today, and make you all feel like you're back at school with us, we're going to start off by talking about the importance of multi-unit residential buildings. Sometimes I jump right to MURBs. We talk a lot about MURBs in our group, but this is what I mean by MURBs. And then we'll get into some of the common performance issues that we see in MURBs and introduce some of the challenges that we're going to see when as our climate begins to change. And then we'll discuss some mitigation and adaptation opportunities in this building stock. But first, I want to start off, anyone who lives in the Toronto area is probably well aware of the news cycle where we're talking about this housing crisis that we're currently facing, even across the country more broadly. And this pressure on our housing stock is only going to grow in the coming years with our increasing population. And we really have a choice here on how we meet this increasingly growing demand. So, age-old question, are we going out into the suburbs, or are we going to go up? Are we going to start to intensify our housing stock? And this decision, while the basis of this presentation is really going to focus on building level performance, I just wanted to introduce this idea that the decision that we make about how we're going to pursue meeting our housing needs in the future goes well beyond what happens at the building level and actually has implications across the broader building stock. It's important to recognize that if these buildings are appropriately designed and operated, and I use that caveat, which I'll explain more a little bit about later on, MURBs can really be an inherently more sustainable form of housing, simply due to their material and space efficiency and the fact that they have less exposed surface area per dwelling unit. But they also support more broadly active and public transportation and keep the costs of urban infrastructure at a per capita level lower than what we would see if we had a more sprawling development like you see here on the left. So in the middle here, I've just got a snapshot from a paper written by some colleagues of mine a number of years ago, but I find this quite striking when you look at the GHG emission impact per person, not just associated with the building operation, but that broader impact of materials, of course, which we'll touch on, and the transportation implications of this building type. So I just want to keep that in the back of our mind. So in meeting the needs of our, the growing housing need, the big question is really whether MURBs are going to be the solution for us. And I have these two images up on the screen because they're predominantly two archetypes in Canada that we tend to see. So the post-war set on the right, on the left, from sort of the 1960s, 70s, and then we're currently in the middle of a second housing boom, which seems to have no end in sight. And so we're going to address these buildings separately. While they do have a lot of shared features, they do have some unique features too, so we'll talk about those. But I think the big challenge that we face here and that we also need to keep in the back of our mind through this whole discussion is that the vast majority of people still prefer detached homes. And we'll go into some of the reasons for this. But in order to really drive this more dense housing, which we know has huge impacts in terms of our GHG emissions, both with respect to building operation, embodied emissions, and transportation related emissions, we need to make this source of housing more attractive. And so really the goal of my whole research program is to not only reduce energy use, but at the same time to really improve the quality of the indoor environment for residents so that this becomes a more attractive place to move to, this type of building form. So let's start by looking at a couple of common challenges that we see across this building sector, and then we'll sort of layer in some of the climate change related challenges. So despite what I just mentioned before about these buildings having the potential to be more material and space efficient, we tend to see incredibly high energy use intensities in these buildings, sometimes higher than single family building types. And so this is a concern which we'll address, and I'll explain some of the root causes of that. But in addition to that, significant energy impact, we also see a lot of discomfort issues, which obviously lead to this potentially not being an attractive source of housing. So thermal discomfort, olfactory discomfort, acoustic discomfort. And then we also need to consider some of the challenges related to high-rise living in the event of power outage. So lack of mobility, elevators not working, water distribution, things like that. So we'll talk about those as well. And then if we look at some of the specific features of post-war buildings and some of our newer contemporary buildings, post-war buildings tend not to have central cooling, which is going to become a critical issue as we start to see our climate changing and growing warmer. We're already at this point in time seeing dangerous summertime overheating, so that's something that we need to address. Pardon me, sorry. And then on the contemporary building side, where we've got these, highly glazed buildings, we tend to see visual comfort issues, lack of visual privacy and glare, also thermal comfort issues related to those highly glazed enclosures. So certainly something that we need to consider. So what I want to do is just delve a little bit deeper into these two archetypes. We've done some extensive field evaluations of occupied buildings. While we do some work in the lab in my group, really the city is my living lab. So a lot of the work that we do is in occupied buildings, which makes our research, I think, really exciting, also somewhat challenging sometimes. But so I want to share with you 2 or 3 studies that we've done, 2 field studies and 1 survey-based study, just to kind of paint a picture of what's going on in these buildings. So one was a study that we undertook. I actually started this when I was wearing a different hat working for the Atmospheric Fund, and was thankfully able to rejoin the study, where we looked at 7 post-war apartment buildings. And we used a combination of resident surveys so we could understand building occupant perceptions and behaviors, as well as monitoring of, what are the temperatures that we're seeing in the suites, as an example. So first, if we look at what the residents told us, there's a lot going on here, but I want to separate on the, oh, sorry, let me just turn on my little pointer here. Bear with me one moment. There we go. So if we look over here on the left-hand side, we can see that across all of our buildings, more than half of residents are reporting that the conditions are too warm in their suites during the summer months. During the winter is a little bit of a different picture. We see a mixture of underheating, so residents reporting that they're too cold, and overheating. But the main takeaway here is that, again, the majority of residents in these buildings that we surveyed are not thermally comfortable. And it becomes rather alarming when we look at what, there we are. When we compare these perceptions to the measured interior temperatures, because we also had some of this objective data. And so we've got a year's worth of monitoring over here on the vertical axis. And then each of these little squares represents 1 day of 1 suite. And so I'll just draw your attention to the legend at the bottom. Anything with a pinky hue is basically in your high 20 degrees C up to over 30 degrees C. And you can see that while overheating is certainly a chronic issue in the summer months, just in sort of the top third of that plot, in some buildings, overheating is a problem all the way through the year. So this is certainly an issue that we need to contend with. And if we zoom in a little bit further, looking at a particular suite, one of the things we were wondering about was how, even in the summertime, we're going to see really nice diurnal temperature swings. How it cools off at night. There's the opportunity to cool that building down, even if it doesn't have central cooling. But what we're seeing is that because of the thermal mass associated with this building type, the temperature in the suites, even with the windows open, really doesn't change very much because there's all that heat built up in the structure over the course of the day. So this is another challenge we need to keep in mind. This is data from 7 years ago. So we're already seeing warmer summers, which are only going to get more severe as we move forward. And shift gears a little bit to olfactory discomfort. One of the other questions we asked the residents was about odors that they detect in their suite. And again, we can see that the majority of residents are experiencing olfactory discomfort at least every day, which is what this signals though, sorry, let me just come back to that. What this is sort of a proxy for is that we have a lot of uncontrolled air movement. So air is not going where it's supposed to, and we're going to come back to that because that's a really key part of the puzzle when we're talking about MERV building performance. So to shift gears from post-war to contemporary MERVs, we conducted a very similar study, again, including surveys and in-suite monitoring, to figure out what was going on in these newer buildings as well. So my question for you, I wonder, you could maybe raise your hand wherever you are, or give me a thumbs up or a thumbs down. Are new buildings any better? I mean, what do you think? I'm sorry to say that not really. We found that in the reported discomfort, about half of residents were still uncomfortable in the winter and the summer. And this is in a different scenario where residents actually have control over their heating and cooling at the suite level. So this was rather concerning. We're also tending to see suite over conditioning of the common areas, which again is another clue that air is not necessarily going where it's supposed to, or that air is being over conditioned, which signals that we have a waste of energy there. And a lot of residents actually reported propping open their windows and doors as well, which again signals that things are not working the way they should. So in addition to those field studies where we looked at post-war buildings and newer buildings, we've also conducted some work on understanding acoustic comfort in MERVs. Because MERVs are unique in a single family home, unless you're attached, like we're in downtown Toronto in row housing, so we do hear our neighbors, but a lot of single family homes don't actually have any of that connection to their neighbors. But in MERVs, you're living above someone, below someone, and you've got somebody on either side. So acoustic comfort becomes a big concern in these buildings with shared walls and shared spaces. So we conducted an internet-based survey of over 200 respondents, and we're, I guess, not shocked, but we're a little concerned to see that the vast majority of MERV residents who responded to this survey were reporting acoustic discomfort, both related to outdoor noise sources and indoor noise sources. And that these acoustic discomfort issues have direct impacts on their sleep, their mental stress, their mood, their ability to study and work, which I'll just flag has become a lot more important. You can see that I'm doing this from my home right now. A lot of us are working and spending a lot more time in their home. And so for people that are doing that in the MERV context, we really have to think about what implications that acoustic discomfort has on their ability to work. And so as a result of some of these effects and some of this annoyance and disturbance, what people are doing is taking things into their own hands and trying to improve the acoustic comfort in their suites. And so they undertake lots of interesting activities, one of which I think is kind of interesting, playing music or TV even more loudly than the noise that they're hearing to mask that noise. And you can imagine that only creates even more acoustic discomfort in these shared spaces. But there are also implications, sort of interdomain implications. So one thing one might choose to do here, I'll just sort of circle, I don't know where my pointer went, but that's okay. One thing people tend to do is weather strip their suite doors. Now, in a lot of buildings, that's where your ventilation air is coming from. It's coming from the corridor. So a measure taken to mitigate acoustic discomfort in this particular instance is actually having a negative impact potentially on your indoor air quality, in that you're limiting the supply of ventilation air. So this is sort of my first hint at what we need to be doing when we're thinking about improving the performance of these buildings. We know we need to address energy, and we know we need to address occupant comfort and satisfaction. But we also need to recognize that all of these systems are interconnected. So one thing you might do to address thermal comfort might impact acoustic discomfort, window operation as an example. Or in this instance, one thing you might do to mitigate acoustic discomfort might impact your indoor air quality. So we need to keep in mind all of the systemic interactions that are happening here. So now that I painted this lovely rosy picture of MERV living, I promise it will get better. Let's also layer in what's happening in the future. So I'm sure everyone on the call is aware of what we're facing as we move forward. And Canada in particular is slated to be exposed to some fairly significant changes in the coming years. And I think this has become all the more real given what happened out west last summer with the heat dome. And this is now becoming a pretty serious public health issue that we need to consider. And if, as I mentioned, within these post-war buildings, many of which don't have any sort of central cooling, and out west, it became quite clear that a lot of people, air conditioning is not common in BC. And when we see what happened last summer, this is something that we need to consider as well as integrating active cooling. So as we face a warming climate, we're of course going to see decreased heating, which is going to have frankly, a positive impact on our natural gas associated GHG emissions, but we're going to see this dramatic increase in cooling requirements as well. And so it's important to consider this energy intensity implication. So I've got, this was a model that we were playing around with, a multifamily building where we were modeling with CWEC, refers to the Canada Weather for Energy calculations. So it's a standard weather file that a lot of building designers would use to model the performance of a building. And we compared that to a future weather file from the 2040s to understand how, if we're designing a building sort of using today's weather, how ill-prepared are we going to be for our projected future weather? And so you can see that there's a huge increase in the space cooling energy intensity, which we need to plan for in terms of our electricity supplies and ability to meet peak loads during extreme heat events. But we also see over on the right-hand side, this is a plot of what we call unmet cooling hours. So normally you would design a system there would only be a small fraction of the year when that heating or cooling system could not keep up with the demand. But based on current cooling capacities under these future weather conditions, we'd see a huge increase in unmet cooling hours, which is a huge concern. And then, of course, we have other elements to factor in here, increased rainfall events and leading to flooding in buildings. And while that's certainly an acute problem, we also need to keep in mind the chronic impacts of wet building materials, if not replaced and repaired properly, can lead to long-term indoor air quality issues. And then we're seeing more and more forest fire events as well, which again leads to the concern. Normally we assume that our outdoor air is cleaner than our indoor air, and so we can bring that in for ventilation, but what happens when you can't breathe the outdoor air? We need to consider how our buildings are going to continue to operate under conditions such as that. And of course, I alluded to this before, high-rise living without power can be rather challenging in terms of mobility, access to water, heating and cooling. These power outages are often aligned with extreme heat or cold events. So we need to consider that and that loss of our mechanical ventilation as well. So now that we have a pretty clear picture of the challenges that MURBs face, and then now we've sort of layered in what we can expect in the coming decades, let's shift our attention to what we can actually do about it. And one thing I want to point out, I'm sure many on the call are familiar with these terms, mitigation and adaptation, but I want to point out first how they are related in building design and operation before we break these down. So building design and operation obviously has a huge impact on energy consumption, which in turn directly impacts our GHG emissions. But then our GHG emissions are what's driving climate change, and the climate change then impacts our building design. So in thinking about how we need to retrofit these buildings, we need to consider both of these mitigation and adaptation lenses. So mitigation to reduce GHG emissions, and adaptation, how we change how these buildings are operated in order to ensure a safe, comfortable, and healthy environment in a changing climate. So looking at the mitigation side of the coin, we're really wanting to do things like reduce our energy demand, and then what demand remains, we want to ensure that we're electrifying and decarbonizing where that demand is coming from. And on the adaptation side, recognizing that we're going to see increasing frequency and severity of extreme heat events, We need to increase our cooling capacity, ensure we have sufficient backup power for life safety reasons, and ensure a robust ventilation strategy that can work no matter what is happening outside. And in the context of this mitigation and adaptation, remember the concept that we talked about at the very beginning. When we look at the broader impacts of GHG emissions related to housing, we also need to ensure that at the same time as meeting our mitigation and adaptation goals, we're also working to promote higher quality, high density housing, which has good indoor environmental quality and design features that make residents want to choose this type of housing over single family housing. So if we start by looking at some demand reduction and decarbonization, what we're going to do is we're just going to step through a couple of examples of passive measures, active measures, and then we'll flip over and look at some of the how we actually meet some of those demands in a decarbonized fashion, or at least reduced carbon, depending on what province you're in and your grid mix. So we'll step through each of these. And what I want to try to do is highlight, so these are all obviously going to have an impact on energy performance and subsequent GHG emissions, but I also want to flag the potential IEQ implications, because again, if we're trying to improve the quality of the indoor environment, we need to make sure that we're improving that for residents. So in terms of reducing solar heat gain, lots of different strategies that we can use here. You know, upgrading windows with different films, using shades and blinds and things like that. Although one of the most effective, which we don't see very much yet in Canada, is exterior shading. So either fixed shading, as you see here on the right, or operable exterior shading, which you see here on the left. And again, we play around with models a little bit sometimes. So we were looking at the impact of these solar control measures. So overhangs, window films, roller shades, and what impact that could have on cooling energy use intensity. And you can see that, you know, while it's certainly reducing that cooling energy use intensity, we're still going to need to deal with some sort of some additional measures to really bring that down. But it does have a significant impact on those unmet cooling hours as well, and has the added benefit of potentially improving visual comfort, reducing glare, brightness, increasing visual privacy. And if we can keep that solar gain down, we can also have the added benefit of potentially improving thermal comfort. And I mentioned when we were looking at the post-war buildings before, we have these natural diurnal temperature swings from day to night. And so we want to try to take advantage of cooler nighttime temperatures to bring temperatures inside the building down to relieve the pressure on our mechanical cooling. So while, you know, the optimal approach would be to have some sort of cross ventilation like you see here at the bottom, we can still look at options like this, the horizontal tilt window you see over here on the left, that introduce two openings even into a single a suite facing a single orientation. So there are certainly options to promote natural ventilation in MURBs. And this has the potential to improve thermal comfort overnight, particularly in buildings that don't have mechanical cooling, can aid in ventilation as well, depending on the conditions of the outside air. Although it can potentially have a negative benefit on, or negative impact on acoustic comfort, because as you imagine, if you open the window on a really busy street, that could certainly impact that overnight, especially. So another passive strategy that we're starting to see a lot more of now is what we call overclotting, which is where we put more insulation on the outside of the building. And also, usually this includes replacing windows and improving the air tightness of the enclosure. Now, this is one instance. There were a lot of questions, and I thank you for those before the presentation, about embodied energy. And this is where, or embodied carbon. And while the focus of this talk is really on operational carbon and GHG emissions, this is the kind of retrofit where we need to really start thinking carefully about the implications that our material choices might have on embodied emissions. And we'll touch on that more a little bit later. But the impact of overclouding and improved air tightness can really have a dramatic impact on our energy use intensity. With a little asterisk, I'll just flag, this is a modeled energy use intensity improvement for this building. We're actually working with this building right now to try to verify the post-retrofit energy use. So stay tuned. I can come back to you and report whether this was actually achieved. But I just want to flag this idea of a building as a system again. So imagine you've spent all this money, millions and millions of dollars, overcladding your building, replacing your windows, really tightening up the envelope. You passed your blower door test, you're all set. But if you haven't done anything about the in-suite heating and or cooling control, and you haven't done anything about the ventilation and providing a reliable supply of ventilation air to your suite, remember that occupants are going to take matters into their own hands. And so we might see things like auxiliary heating and cooling equipment. We might see people opening their windows in the middle of the winter, trying to get more fresh air, more outdoor air. And so when you're considering a retrofit like this, it's really important to consider the broader building systems and components and how they're all going to work together, because you certainly wouldn't want to spend all of this money and then all of that, energy savings goes out the window, pun intended, when your occupants are taking matters into their own hands. And again, this is driven by an energy benefit, but there is the potential, if done well, overclouding can really improve the thermal comfort and the acoustic comfort, because you're really, wherever air moves, so does sound. So that has a nice side benefit as well. Now we're going to come back to my favorite topic. We spend a lot of time talking about something that's invisible, which is interzonal air leakage. And what I mean by that, and if you think back to our olfactory discomfort that I mentioned a couple of slides ago, all of those odors coming from other suites are a sign that air is not going where it's supposed to. So exhaust is not working as it should. Pressurized corridor ventilation systems are not keeping those odors within suites. And so we've been focused, as we improve the energy performance of our buildings, we've been really focused on enclosure air tightness. And what I mean by that is windows and walls. But what I'm really advocating for is more attention being paid to interzonal air leakage. And this is one of my PhD students' work, which I'll just explain what's going on here. So normally with interzonal air leakage, we test a single suite in what's called a compartmentalization test. And you're basically trying to make sure that the suite enclosure as a whole, the floor, the ceiling, the walls, and the exterior wall are all relatively tight. We do that just by testing a single zone, and it's actually relatively easy to pass that test. But what my PhD student was working on is actually looking at each of those 6 sides of the suite separately, and noted that the air tightness of those boundaries is very different. And so this can have a huge impact. You can see that if we have the requirements here in the red line, that the corridor walls, and this is not including the doors, vastly exceed those requirements. And if anybody is interested, I can talk to them offline about why this is. But that's certainly contributing to uncontrolled air leakage. And what you're seeing over here on the right-hand side is some work that was done out in BC, where the researchers actually tagged the ventilation air with a tracer gas, which is the concentrations of which you see here in blue, just to look at where that ventilation air was going in these large multifamily buildings. And you can see by the shading of the blue that the upper suites are actually getting a lot more outdoor air than the lower suites are. And this makes sense. We're fighting, you've got ventilation air that's being pushed down into the building by a fan, and you're fighting against what we call stack effect. We've got that rising warm air in the building. So you've got these pressures fighting against one another. Getting air where it needs to go in a tall building is a very challenging prospect. And so we're kind of seeing hints at this through these data. And so we've been, again, playing around with some models. This is not yet peer reviewed. This is something hot off the presses just for you today. But something that I wanted to point out, what we're looking at now is, rather than focusing on the enclosure air tightness, which is very important from an energy perspective, we also need to be focusing on the interior partitions. And so we were playing around with the air tightness of different enclosure or different partition types. and found that simply by paying attention to the to the stairwell doors, and really the elevator doors are the big one, we can really dramatically reduce interzonal air leakage, and as a proxy, our thermal energy demand. So just what I mean by this is, something like, and I'm sure you've seen this in office towers, you'll often have a vestibule around the elevator shafts, and that's really to break up this large vertical shaft where you've got air easily moving back and forth through the elevator shaft. So if we can get that under control, then we can do a much better job of getting air where it needs to go. And you can see I can't talk enough about interzonal air leakage, but in addition to all of the energy benefit, it also has the potential to really impact a lot of the other performance issues that we're seeing in MERBs. So that olfactory discomfort can be addressed. Acoustic discomfort, I mentioned wherever air goes, sound is also going. So if we can better control that, we can improve acoustic comfort and thermal comfort as well. So this is something I think we really need to be paying attention to. And then if we shift from sort of the passive options over to some of the more active systems, because our modeling has shown that, even if we do everything right from a passive perspective, in our changing climate, we're still going to need active strategies to maintain thermal comfort in these buildings. So there's some recent work out of UC Berkeley that's been looking at the use of fans and how far we can get with fans in terms of improving thermal comfort during heat waves. So this is something that we tend not to see very much in multifamily buildings, in MERBs, but something that could be used more widely, especially if you have the appropriate floor to ceiling height, which is not always the case. And that, of course, has the huge potential and the driver to improve thermal comfort. And then going back to our post-war building friends, recognizing that we don't always have the luxury of having in-suite controls like we see in newer buildings. And installing this on a per-suite level is incredibly expensive. So we've also been exploring ways in which we can perhaps strategically place fewer control valves through the suite and use wireless temperature sensors or a smartphone app to control groups of suites instead that are experiencing similar temperature conditions. So we did a little modeling with this, and while there's quite a range in terms of payback period, we tried out lots of different strategies for placing these valves. There is the potential, accompanying, I'll just flag our green options here, which are probably the most palatable to building owners, somewhere in the 10-year payback range. We can still see a fairly significant energy reduction in and around the 10 to 20% reduction, but a huge improvement in overheating. So really reducing those instances of wintertime overheating by properly controlling these grouped suite arrangements. So this is something that we've been working on as well. And that, of course, has the potential, obviously, on the right-hand side, significantly improving thermal comfort, but also adding that ability for occupants to control their spaces, which means they're going to do, ideally, have less, auxiliary heat or heating equipment and other equipment within their suite. So for the buildings, though, that do have in-suite controls, some of you may be shocked to find out that a lot of new MERBs have non-programmable thermostats in them. So one relatively quick and easy off-the-shelf solution is to employ smart thermostat technology in these buildings. And I'm not promoting the one on the upper right here. It's just an example of what one of these look like. But one of the big benefits of smart thermostats is a lot of them have an occupancy sensor in them. So even though you may have programmed your thermostat to, for the most part, follow your comings and goings, the occupancy sensor can actually detect when you're not there, perhaps when you said you were going to be, and dial down that set point temperature in order to save energy when you're not there. So we undertook a study of this. We hijacked people's thermostats and they let us come into their suites and replace their non-programmable thermostats with programmable thermostats, and saw that really high programming rates were achieved in these, probably because the user interface is a lot easier to use. I don't know if anybody's ever tried on those push button thermostats, incredibly difficult to program. But one of the exciting things was that this occupancy-based control that I mentioned can really significantly reduce avoidable demand. And so what I mean by that is demand when you're not home is dictated by your program. Can we avoid that from the as scheduled scenario simply by introducing this occupancy-based control? And one of the really interesting things about the study that we found, which was not expected, was that in a MERB context, unlike in a single family home context, you can network these and actually use this to diagnose performance issues within the building. And so it was by analyzing the thermostat data in these two buildings where we were doing the study that we found that the central systems were actually over conditioning, so leading to a waste of heating and cooling energy, which was actually impacting the thermal conditions in the suite. So that was kind of a win-win on the energy and thermal comfort side to address that single problem. And then again, sort of the last active strategy I want to talk about is coming back to that idea of decarbonization. So for those that are unfamiliar, I know out west you tend to use electric heating, but in the Toronto area and in Ontario more broadly, and across a lot of the country actually, we tend to use natural gas for our space heating and our domestic hot water heating. And in residential buildings, space heating makes up about 50% of the energy that we require, and significantly more of a larger proportion of the GHG emissions. So getting off of that GHG emission intensive fuel is really a big move over to reducing that building level GHG emissions. So this is also hot off the presses. One of my undergraduate engineering science thesis students was exploring how we introduce active cooling into these post-war buildings. And so what we often see is units called PTACs, for those that are unfamiliar. Those are just the little window units that you put in each suite, or the little floor units. But what would happen if we introduced an air source heat pump? And what would be the cost associated with introducing those air source heat pumps? And we can see that there's a significant reduction in the energy associated with providing that space cooling, although it's a more expensive option at this moment in time. As we look to the future and some of the weather that we're going to see with our changing climate, it actually becomes a more economical approach. So this is really exciting, and I think we're going to see a big shift to air source heat pumps in the coming years, particularly in the retrofit context. And these have the nice benefit too of not only switching our space heating fuel source from natural gas to electricity, they also provide added cooling where perhaps there wasn't that ability in the past. So if we look more broadly, just kind of zoom out from some of these ideas, really we want to be addressing both mitigation and adaptation at the building level by really two fairly simple steps. I say there's a lot of little sub-steps in here. We, of course, want to reduce demand and at the same time increase resilience to some of those extreme weather events that I mentioned at the beginning. And then, as much as possible, electrify our supply and get off our fuel source, or our GHG intensive fuel sources. So all of that discussion so far has really been about operational carbon. And what I do want to flag here is that as we get more high performance buildings, lower energy use, the embodied carbon piece of the pie becomes a larger part of the conversation. There has not been a lot of work done here in the retrofit space. One study that we were involved in was purely a mechanical retrofit, and the embodied carbon to life cycle carbon savings really made it a no-brainer. But once we start to get into overclotting retrofits, which I flagged before, that's really where we start to see we need really careful consideration of the materials that we're introducing into this. So we really need more data to start informing what this looks like, and we're working with some partners on this. This is a direction that we're going to spend a lot more time on in the coming years. But what I was encouraged to see actually just last week or the week before was a report on new building embodied carbon tracking, which was done by Mantle, and I think the City of Toronto and TAF were involved in it. So this is the kind of data that we need, but on the retrofit side of things, just to start, this is how energy performance monitoring started, 20 or 30 years ago. we had no idea what our buildings were using. And now a lot of people can probably cite what the energy use intensity of their building is, or at least I hope you all can on the call. And so the point is, we can't manage what we don't measure. And so if we don't have a sense of, if we don't start collecting this embodied carbon data, we're never going to be able to manage it. So this is sort of a keep your eye on this space moving forward. It's certainly going to be part of a lot more conversations in the future. So just to now zoom out completely, just a couple of things that I want to leave you with today. I hope it's clear, building performance issues are really a growing concern, but we need these MURBs in order to meet our housing demand. And so we need to start addressing the occupant experience while also really significantly reducing GHG emissions in this sector. And keeping in mind that with our changing climate, we have to ensure that they're safe, comfortable, healthy for these residents. So it's really kind of this trifecta of an opportunity, but also a series of challenges that we need to address holistically. So I would advocate for really, I hope it's clear through some of this discussion how interrelated some of these systems are. Some of the ways that I'd like to see this really being addressed are thinking about the air movement first, getting ventilation and that uncontrolled air leakage under control. Then we can start to talk about the enclosure and the in-suite controls. And remember that those really need to happen together. Otherwise, you're going to get occupants, not intentionally, but overriding some of those energy benefits you might see with an enclosure retrofit. And then we want to make sure that we're decarbonizing our mechanical systems and adding that active cooling to deal with those extreme heat events that we're going to see coming forward. And while we're focused on GHG emissions and energy performance, we set goals for these things when we're building new buildings, when we're retrofitting buildings. Integrate comfort goals in there as well, and goals related to the indoor environmental quality, because if you haven't got a goal, it's not going to be part of those discussions as you're moving forward with the design of retrofits for these buildings. We also want to get the most bang for our buck. So looking for retrofits like that interzonal air tightness that really address multiple performance issues. And also remembering that we need to consider this life cycle carbon. And if you're interested in this, I have colleagues that are working on it. We're starting to work on it, and we've got some tools that might be useful for you. So just to make you feel like you're back in class, I've got some homework for you, should you wish. These are just a couple of resources. If you find this, this type of discussion really interesting, I would really recommend, there's actually 4 resources in here. The first is from the University of Waterloo, just an interesting read about what we as Canadians are going to be facing in the future. The second point here are 2 design guides, one focused on thermal resilience and one more broadly on MURB design. Strongly encourage you to review these if this is your workspace. And then the third one is also sort of hot off the presses. ASHRAE just released an energy design guide specifically for multifamily buildings just in the last few weeks as well. So some reading for you there. And just as a last comment, I just want to acknowledge all of the students and my colleagues who've contributed to this work. This is many, many, many projects over many, many years. So thank you. Thanks, class. Happy to take any questions.
Great. Thank you, Marianne. We've got a number of questions that have popped up during the course of your presentation. I'll begin with the first one, which was from an anonymous attendee. The question is, given that artificial cooling of interior spaces creates heat in the outside, has any research been done regarding how to stop this vicious cycle?
Yeah, that's a really great point to whomever that anonymous person is. And that's one of the big contributors to urban heat island effect as well. We've got all of these heat generating activities that are happening in cities, and it is absolutely a vicious cycle. From a mechanical standpoint, I don't know what's being done about that, but I know there is a lot of research on greening urban spaces and trying to reduce that urban heat island effect. That's not something that our group does. Because if we can keep, it's kind of, that would be one way to break that vicious cycle, because if we can keep urban temperatures lower, then people have to space condition less, which means there's less of that waste heat contributing to the urban heat island effect.
Thank you. The next question is for Bruce McGregor, who asks, have your studies also looked at comparative waste diversion practices for high-rise construction?
No, that is not. We don't really do construction management research, although I do have some colleagues who are working on that. So I'd be happy to, if you get in touch with me afterwards, I can certainly connect you with them.
Okay. Next question is from Christina Ismailos, who asks, given that power outages can occur during extreme weather events, such as heat waves, winter storms, what are the resilience consequences to switching to fully electric heat pumps? How do we address homeowner concerns about reliability?
That's a great question. And hi, Christina. Thanks for the question. This is something that we were actually talking about in our group this week. I think from an extreme heat perspective, this is really where we need to think about passive measures and ensuring that we can get as far as we can from a comfort perspective with exclusion of solar gains through good solar control and promoting natural ventilation. And unfortunately, in a lot of our existing MURBs, this is really challenging because they're single-sided. So we need to really rethink how we're designing new MURBs to better promote that. From a reliability perspective, this is going beyond my direct area of research, but one of the really exciting things that I see with EV, electric vehicle integration in a multifamily building is we can use that at least in the short term, like in an emergency, as a bit of a backup power supply. So you've got, when we see broader adoption of EVs, it's like you've got this giant battery sitting in the basement of your building. And if used strategically and judiciously, could potentially be used to really power some of those critical systems like space cooling. The other unique thing about MURBs, though, is we don't necessarily, in an emergency situation, we don't necessarily need to condition the whole building because we have the benefit of common area spaces. And so what we're seeing already in buildings that don't have central cooling, we're seeing cooling centers being created in these common area spaces. So at least people can have a space, a refuge space. Because one of the critical things about the human response to extreme heat is that prolonged heat exposure. So it's not only related to the temperatures to which you're exposed, but how long you're exposed for it. And so if you can get a bit of a refuge and cool off for periods of time in an extreme heat event, that can make the difference between life and death, frankly.
Thank you. The next question is from Andrea Body, who asks, is there a role for thermal mass in new builds or even in overcladding solutions?
That's an interesting question, Andrea. One of my colleagues a number of years ago was looking at whether it made sense to add additional mass for mass sake, like for the thermal benefits of thermal mass in terms of flattening your cooling load. And if I recall correctly, he found that the existing typical slab thicknesses in MURBs, there's not much added benefit to going further beyond that. So we already have a reason. This is, you can tell it's a little bit outside of my area of expertise, but from what I understand, I don't think there's much benefit in going beyond what we already have, assuming you have a concrete superstructure. Now, if we move to wood frame buildings, I think that's, from an embodied carbon perspective, that's a whole other discussion. But I think you need to more carefully consider the benefits of thermal mass in a less massive building like that.
Thank you. The next question is from my Lunch and Learn colleague, Jim Courtney, who says he watched the presentation on the concept of using lithium-ion storage in residential buildings to assist with addressing electricity demand. Solar arrays have excess energy generation that can be put back into the grid. So the question is, have you looked into the potential for energy storage as one way to minimize climate impact?
Yeah, thanks, Jim. We haven't looked at that specifically, but that kind of connects back to Christina's question about reliability as well. And if we can have storage within at the building level that can potentially help us not only ride out emergency power outages, but can also potentially be a place to store that excess solar energy for sure. But that's a little outside my area.
Next question is an interesting one from Paul Milgram, who asks, does cooking add a significant contribution to the factors that you deal with? Is cooking with gas very common in MURBs? I'm thinking of the news last week that reported an adverse effects of gas cooking on indoor air quality. Finally, if the way we cook really does make a significant difference, is there a move to introduce more induction cooking into MURBs? A very timely question.
Yeah, that's great. Thanks, Paul. Yeah, I heard that piece as well. Natural gas cooking appliances are not common in multifamily buildings. They tend to be your typical electric resistance burners. But yeah, absolutely. I mean, in the event that there was, that would certainly have a big impact on the indoor air quality, as we've seen from this most recent research. And I would certainly, well, yeah, I would. From a broader cooking perspective, not natural gas, I think it's more of a concern with that the odor transfer between suites and what that's indicative of. But yeah, natural gas isn't really used very much in MURBs.
Next question is from Brian Lawton, who asks, in the Ottawa area, there has been a significant exodus from MURBs to the suburbs and beyond in spite of intensification policies for local government. Given that this pandemic likely is not the last, God forbid, and the fear of MURBs living likely will not reduce, how can we make MURBs sufficiently advantageous from all aspects of government, all unwilling to mandate it?
Oh, that's a loaded question. From a policy perspective, I don't know where you go with that. I think from an improving performance perspective, there are a couple of things that I didn't touch on, which are outside of my area of research directly, but I think thinking about this pandemic, we need to put a lot more thought into ventilation and that uncontrolled air movement piece, of course, because I think what leads to that discomfort is the idea of shared air, particularly in a pandemic. So there's that piece, but I think there's also a problem, access to outdoor space, access to common area space, and the size of the suites are huge reasons why people will make the move out to the suburbs. And until we can offer an experience that's more comparable to, what you might have in the suburbs in terms of access to outdoors, I don't know if we're going to get there. And that is, I think, really a conversation that we need to start having with developers. Like, what is it that residents really want, and how do we keep them in the city? Sorry, that doesn't completely answer your question, I realize.
I think we are nearing, in fact, we're past the top of the hour, so I will pass on one last question from Ernesto Springola, who asks, can you comment on the use of photovoltaic windows to generate power, reduce glare, and insulate? Are these too new to be considered? Thank you.
Thanks, Ernesto. To be honest, it's not something that I've looked into yet. From a purely, I'm always kind of keep it simple. I'd be inclined to focus more on passive systems first and really make sure that you're putting photovoltaics where they're going to get the best access to solar gains. So that might not be on the walls of a building which is located in a fairly dense downtown area. So I think they need to be used judiciously. And in terms of dealing with glare, frankly, I think the better approach is exterior shading or interior shading if you don't have access to that.
Thank you. Now I shall begin my closing remarks. First of all, thank you to everybody in the audience for all of the questions. Unfortunately, time did not permit us to address them all. Before we close, I would again like to thank Professor Marianne Touchie for being with us today. Thank you for such an informative and fascinating presentation on the future of high-rise housing. To everyone who joined us here today, we invite you to share your feedback on the Skule Lunch and Learn series. A link to the online survey is being made available in the chat box at the bottom of your screen and will be shared with all of you after this event by email. A link to the presentation will also be shared with all registered guests early next week, many of whom were unable to be with us today because of time differences around the world. The Skule Lunch and Learn events are traditionally hosted on the second Wednesday of each month from October to May of each year. Today's presentation is our final event of the 21-22 Skule Lunch and Learn season. However, we look forward to resuming the new season, hopefully once again in person at the Faculty Club in October 22, and we'll be sharing more details about our upcoming speakers later this summer. Furthermore, I would also like to acknowledge and thank TD Insurance and Manulife, both of whom are sponsors of our Skule Lunch and Learn through the U of T's Pillar Sponsorship Program. If you are interested in learning more about Skule Lunch and Learn series, please contact the alumni office by email at events@engineering.utoronto.ca. In closing, I would also like to thank all of you for joining us for today's presentation and hereby adjourn today's last presentation of the 21-22 Skule Lunch and Learn season. I hope you all have an amazing summer wherever you might be in this world, and I look forward to seeing each of you again, hopefully in person in October. Thank you and enjoy the rest of the day.